Okay, let's go ahead and get started. Let me make sure that that's actually recording. Yeah, it is. Okay. All right. So, I'm not sure how much of what we did before break has gone away out of your brains. But before the break, we were talking about isotopes. You guys remember that? So how many protons, electrons, and neutrons does something have? And if you have an isotope, then it's going to be different versions, or isotopes are different versions of an element. What's different about two isotopes of an element? So for example, if I say I've got carbon 12 versus carbon 14, those are two different isotopes of carbon. What's different about those two isotopes?
One's greater.
Okay, one's greater. They have different masses, okay? But why do they have different masses? It's not the electrons. Electrons are actually so small that their mass almost doesn't count. It's not that they're small necessarily, but they don't have hardly any mass whatsoever, okay? So it's not that. Now another way that I could write this might help you out a little bit. This is carbon 12, and this is carbon 14, okay? Now what's that bottom number telling me? You remember? Okay, the bottom number is the atomic number, which is the number of protons, okay? So the number of protons, notice, in both of these is exactly the same, right? So if the number of protons is the same, what's different between the two isotopes? The number of neutrons, okay? So isotopes have different numbers of neutrons in them. Yep. No. Okay. So I just wanted to do that little review because that sort of explains the idea, or helps explain the idea of average atomic mass, okay? So atomic mass units, AMU, just by definition is 1/12 the mass of a carbon-12 atom. 1 AMU is 1/12 the mass of carbon-12. Okay. Now, if you look at on the periodic table, carbon-12 has a mass. Well, actually, you can't look on the periodic table. The mass of carbon-12 is 12. So what's 12 times 1/12? Let's see how we're doing on our math here. 12 times 1/12 is 1, right? Okay. So when they were trying to figure out, basically the reason for the atomic mass unit is because if you measure the mass of one atom in grams, it's going to be really, 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 really small, right? Does that make sense? The mass of one atom, if you put that on a balance and you tried to weigh it, do you think that our balances would weigh one atom? Probably not, okay? Because that's going to be really, really small, okay? So they came up with this unit called the atomic mass unit that allows us to more easily talk about the mass of an atom. It's a really small unit, okay? So the mass of one proton or one neutron is equal to 1 AMU. Not exactly, but close, all right? Close enough for our purposes. So one proton is about 1 AMU, one neutron is about 1 AMU, okay? So notice carbon-12, that's the number of protons plus neutrons, right? So that has a mass number of 12, so its mass is 12 AMU. Does that make sense? Okay. An atom's mass, I don't know why this bothers me. Should be an apostrophe there. An atom's mass depends mainly on the number of protons and neutrons it contains. Okay? And I kind of just said this. The number of electrons in an atom, that doesn't really affect the mass very much because the electrons are so light as far as their mass. Much lighter than a proton or a neutron. Okay? All right. So, now we're getting to the reason that the masses on the periodic table are decimals instead of whole numbers. Because it seems like if we're just adding up the number of protons and neutrons, then those numbers on the bottom should be whole numbers, not decimal numbers. Okay? But they are decimals. And the reason why is because it's the weighted average of all the isotopes of that element. okay? So let me give you an example of that. That explains why the masses on the periodic table have decimals. Tell you what, before we get to this, I want to show you an example of this based on the way that I calculate your grades. Okay, and when I say I calculate your grades, I mean this is the way that the grade book calculates your grades, but this is the way I would do it by hand if I was doing it myself. In order to do this, I'm going to have to remember exactly what your grading scale is. Is it 50% for tests? No, I don't think it's 70. Here, tell you what, I'll open that document just to make sure I get this right. Just in case you're interested in how I actually calculate. Okay, so the grade breakdown here, there we go. Tests and projects are worth 50%, your labs are worth 25%, and your quizzes are worth 25%. All right, so that's your grade breakdown. So let's say, just theoretically, let's go back to this. Oops, what did that do? Okay, so let's say that theoretically, in this class, you have gotten a 85% on your tests. Okay, that's your score on your tests so far. And then you've gotten, I don't know, let's say you've done really well in the labs. You've gotten 100% on your labs. You've just gotten every single point on the labs. I don't think that usually happens. I don't know why I'm using that as an example. But 100% on the labs, and then maybe 70% on the quizzes, because maybe the quizzes, you still hadn't quite learned the material yet. By the time you get to the test, you've got it a little bit better, so you're doing better on tests than you are on quizzes. All right? And let's say that, so that's your overall grade, or your grade breakdown, I guess. And we want to know what is your grade in this class right now. Okay? So the way that I would calculate that, this is a weighted average. It's a little bit different than a normal average. Okay? What would I normally do if I wanted to find the average of these three numbers? Yeah, you just add them up and divide by 3, right? Okay? That won't work when you're calculating my grades in this class, okay? Because the grades that I give you are a weighted average, okay? So what I just told you was that your grade in this class is 50% tests, 25% labs, 25% quizzes, all right? What that means is this number is more important than the other numbers because it has a greater weight, okay? 50% of your overall grade comes from the score that you get on your tests. So the way I would figure this out, I basically take 85% and I multiply that by the weight that I give it, okay? The weight that I'm giving it is 50%, but I'm going to change that to a decimal, so I'm going to change that to 0.5, okay? Then I'm going to add that to your lab percentage. Now this is weird. You probably have never calculated an average this way before, but this is another way to calculate an average, okay? So then I would add that to the 100% that you got on your labs, and your labs are worth what percentage again? 0.25, 25%, or 0.25, okay? And then I would add that to the 70% that you get for quizzes, and multiply that again by 0.25 because the quizzes have a 25% weight, okay? So then what you would do is you would basically multiply that and add it all together, okay? So I'd take the 85% times 0.5, then I would add that number to 100% times 0.25, and then I would add that to the 70% times 0.25. And that actually ends up, I didn't plan it this way, but that ends up giving me an 85% overall grade that you have in the class. No, the percentages you can keep the same because you want a percentage at the end, right? Now, it might not be a whole number, it just kind of worked out that way this time. Okay? Yes, sir? I do not, sorry. He was asking about tissues, in case you're wondering on the video, and I said I didn't have any. So, well, people comment on the video sometimes. Please restate the question that you're answering because we don't know what the question is. So, not that was really that important of a question for me to restate, but anyway, point is, the tests are worth 50%, so we might expect our overall grade to be a little bit closer to this 85% than it is to the other two numbers. in this case, it's right at 85%. Now that just happened because of the numbers that I picked here. Okay, that was just kind of by chance. But that's how you calculate a weighted average. Now, if you had just taken these three numbers, 85 plus 100 plus 70, and divided it by 3, see, this is a bad example because you get 85%. I just picked numbers that worked out a little too nice and neat. But usually when you add these three numbers up and divide by 3, it's not going to give you the same number as when you calculate the weighted average this way. Okay? All right, so that's a weighted average. And that's actually what they do when they're calculating the number that they're going to put for the mass on the periodic table. Okay? So for example, atomic mass of chlorine is 35.453 AMU. Okay? Now, the reason for that, in nature, chlorine is about 75%, a little bit more than 75% Cl35, but then the other 25% or so is chlorine 37. Okay? So what you do is you do a calculation much like the one that I just did for your grades. Okay? You calculate the weighted average, and that would give you this number of 35.453. Let me see. Is there a place for you? Is there a huge space there? Okay. So the reason that that space is there is because I want to basically show you how to do this calculation. Okay. So we've got 75.770% chlorine 35. Okay. Now this 35 right here, that's the mass of chlorine 35. Okay. Because remember, that's the number of protons plus neutrons. Okay. And each proton and neutron is about 1 AMU. So chlorine 35 is 35 AMU for the mass. Okay? So what we can do here is take 35 AMU times the percentage. Okay? Which this percentage, just like I did when I was doing my calculation before, we're going to change that to a decimal. Okay? So we're going to change that to 0.75770. A lot of sig figs there. Okay, and then what we're going to do is we're going to add that to the chlorine 37, which is 37 AMU, times 0.24230. Okay? When you do that calculation, then you end up getting, that's a little different. Make sure I punch my numbers in right here. 37, 24230. Yeah. I don't know if our percentages are a little bit off here from what they're supposed to be or what's going on, but the number I'm getting. Oh, does it?
Yeah, like at the top, it says what you have there, and if it's mass of chlorine 35 equals 34.
Oh, okay, that's what it is. Okay, so the mass of chlorine 35, what's the actual mass on that one?
It would be
34.969. There we go. Okay, so remember, one proton, one neutron is not exactly 1 AMU, okay? So I was being a little bit imprecise there.
And then 37 is
36.966. Okay, thank you. So that should work out better. Okay? And they will give you, in any sort of atomic mass problem that you have to do, they will give you these numbers. All right? So basically what we're doing here is taking the 34.969 times 0.75770, add that to the 36.966 times 0.24230, and there we go. That's better. Okay. So then when you round that, we've got 5 sig figs in each of these numbers. So when we round that to 5 sig figs, it gives us 35.453 AMU. Okay? So that's how those numbers on the periodic table get calculated. It's based on what isotopes exist in nature, okay, and how much of each isotope is there. So what this is saying, basically, if I can collect a pure sample of chlorine from the environment, okay, let's say that I can get a pure sample of chlorine from somewhere, and then I analyze that pure sample of chlorine, we would expect that about 75% of it would be chlorine 35, the other 25% would be chlorine 37. Okay? Now how in the world do we separate those from one another? I mean, how would I be able to know the difference between 35 AMU versus 37 AMU for these atoms? Because that mass difference is really, really small on the atomic scale, right? How would you separate something that's heavier from something that's lighter? Okay. Okay, maybe if it, like some of it sinks down further, possibly. Is that what you're thinking? Something along those lines? Okay. So you could do it based on, if you've got a mixture of it, what sinks to the bottom, right? Because the heavier stuff usually sinks to the bottom. Okay. So that could work, potentially. But we still have to have some way of being able to count the number of each type of atom, which is difficult, okay? Yeah, scale's probably not going to work very well for us here either. Again, because, how do we know the difference between the two? So what they actually do, they have and this is, not that you really need to know this, but it's kind of interesting. They basically have a machine that they can put this through called a mass spectrograph, or mass spec, if you're cool. You just shorten it. And they basically shoot the chlorine through this tube, okay? So the chlorine goes through a tube, and then they have, see, I'm going to have trouble drawing this. But basically they have an electric field, okay? So put a positive on one end, negative on the other end, okay? As it goes through here, they blast this with energy so that it becomes an ion, so it has a charge, okay? And so then what happens is, these things that are now negatively charged, they're going to deflect a little bit. And they have a detector back here that can measure where things hit on the detector. Okay? So the chlorine 35 is a little bit lighter, so it will actually deflect more and might hit up here on the plate. The chlorine 35, or 7, is a little bit heavier, so it won't deflect quite as much, so it might hit right here on the plate. So they can measure based on how much of the atom is hitting up here versus how much of the chlorine is hitting further down on the plate, and they can actually tell, okay, here's how much 35 we have, here's how much 37 we have. Okay? So kind of an interesting technique they can use, and that's how, if you're into forensics or anything like that, they can use mass spec to identify unknown compounds. So you find an unknown white powder next to a dead body, like they always do in the crime scene investigator shows. They can run it through a mass spec like this, and they can figure out what exactly is in it, based on how much it deflects, because they know how much each weight is going to deflect. Okay? So just kind of an interesting thing. Not that you really need to know that, okay, but that's how that works. So basically, once you know your percentages of each of these things, you can just plug it into this formula, and that will give you your number, and that's the number that goes on the periodic table. Okay? That's where those decimal numbers come from. All right? So this is an important question. Make sure that you understand this. And you might even jot this down somewhere. If I ask you, what percentage of chlorine has a mass of 35.453 AMU, what are you going to tell me? What percentage of chlorine has a mass of 35.453 AMU? 35.453. It's just the number that's up there on the periodic table. Or actually, it's right here. Okay. What percentage of chlorine would have a mass of exactly 35.453 AMU? Any ideas on that one? Probably better that you don't answer this because it's a trick question. Because 0% of chlorine has a mass of exactly 35.453. Why? What is this number? It's an average, right? There is no chlorine that's exactly 35.453. That's the average of the 35 and the 37. Does that make sense? Okay? So if I ask you that question, now you've been warned, okay? If I asked you exactly, well, what percentage of this atom has exactly a mass of 35.453, you're going to tell me 0, because that's an average. That's not the mass of any of the chlorine atoms. That's the mass of the average of the two types. Okay? All right, let's see what else is on here. Wait. Oh, yeah, that's what I should have done. Oh, okay. So the equation here, which can sort of complicate things sometimes, but this is what we basically just did. Yeah, it's a little complicated. So if you can just remember what we just did, that might be helpful. But basically, average atomic mass is equal to the mass of one of the isotopes. Okay, so in our case, the mass of the chlorine 35, okay, which was 34.969, times the percent abundance, which we said that the chlorine 35 was 24.230% abundant, divided by 100, okay? In other words, I basically took that percentage and I changed it to a decimal. Okay. Well, if you know how to change a percentage to a decimal, you don't have to worry about the divide by 100 part, but that's how you do it, okay? That's how you change a percentage into a decimal. Does that make sense? Okay. So then, same thing, then you add the mass of the second isotope times its percent abundance, which needs to be in decimal form. Okay? All right, so that's the basic idea there. You plug in the numbers. So if you plug it in, that's what it's going to look like. Again, I just changed this immediately to 0.75770 instead of dividing by 100, and then 0.24230 instead of dividing by 100. But this is the actual formula. Okay? So then the answer, when you round to the right number, sig figs, would be 35.453. All right, so that's it for atomic mass. Now the only thing that I will say, because this can be a little confusing, we already learned that those numbers, those decimal numbers, meant something else. We learned that earlier. What else did we learn that decimal number is supposed to represent? The molar mass, right? The number of grams in 1 mole of an atom, okay? For reasons you don't have to worry about in here, the molar mass and the atomic mass are basically the same number, okay? So if I ask you about the atomic mass, you're going to tell me that decimal number. If I ask you for the atomic mass of calcium, you're going to tell me 40.078, because that's the decimal number that's up there, okay? If I ask you for the molar mass of calcium, you're going to tell me 40.078. The only difference is, if I ask you for the atomic mass, it's 40.078 AMU. That's your unit if I ask you for atomic mass. If I ask you for molar mass, it's 40.078 grams per mole. Okay? You just need to be aware those are the same number. Okay? So regardless of which one I'm asking you for, you're going to give me that decimal number that's on the periodic table. Okay? All right. So that's that. We're just going to do some practice on this, and you will have a quiz over this first thing tomorrow at the beginning of class. So we actually have some time to do this practice today, so you can make sure that you've got it before you leave, which is good. Yeah, we do. We have about 20 minutes, I think. So that might be enough time for you to finish the whole thing in class. These take a little while, so we'll see. But anyway, I would work on that, and then check your answers with me to make sure you're on the right track, and then you might not have a whole lot of homework tonight to get ready for your quiz tomorrow. And then tomorrow we will do a lab after the quiz.